Yes, ma'am.
Okay,
I can hear you, but I don't have very much voice.
Well, I'm sorry. You are, I think, one of our only first early testers, so like January, December testers. So let me address your questions about 2.4, which was the West Point Bridge Builder software. That is free and to be downloaded. And you want to just make sure you get the most updated version of that. And you also want, if your kids are going to download that, you want to make sure that they also download the same version, because the prices are different depending on the years. So, like, I didn't realize that the first year, and I had kids that had old versions, and their bridges were so much cheaper than kids that had the new version. I have to be really honest, Jennifer, I only do the West Point Bridge Builder activity if I have a sub day.
That's pretty much across the board, too. A lot of people do that.
My kids do it in middle school in their tech class, and so most of them have seen it. So it's kind of my backup sub plan, as opposed to something that I can do. So most years I don't do it. And then you had a question about Robot C. Do you have the Robot C loaded yet on your computers?
The old version, and I'm not sure you can hear me, but the old version, or there's a mishmash as I was going around our student computers today. Some had a periodic version and others had a trial mode, but none of them are accessible except minimally. They can go in and look at tabs, but they're not functional. They can't enter anything into it meaningfully or test anything that we build.
Okay. So when you paid for your project Lead the Way, and Adam, correct me if I'm wrong, you paid for access to that software.
Correct, yeah.
So you have to, as a school, request your Robot C license, and then they will send you a code, and that code will then let your tech people or you, whomever, load Robot C on all of your computers.
And that code represents not a 10-day or a 30-day trial. That represents full access.
For a year.
Okay. I think one of the, I'm not going to call it a problem, I'm going to call it an opportunity that I'm seeing is that there's so few Project Lead the Way teachers in our county that they don't designate one person to handle Project Lead the Way or to be the liaison, and everybody's out there fending for themselves. And so there was no communication to us about the software needing to be updated. And I certainly didn't know, and none of the APs knew. And so when I got to it in the curriculum, I didn't know what to do, and I started looking for it. And around the same time, I started registration at Duke. And it's all there that you have to download it and then get the license number when you go to training, and it just kind of mushroomed. So I don't know what to say except I've got 3 weeks left, and I'm trying to, like today, we did other things with coding, which is a lot of what the Robot C is the way that I understand it, is programming the robots to do things. So I found other ways to address coding, but I'm not sure that they're going to get totally what they need, but I'm trying.
Right.
So
definitely make sure if you're using some coding that you are including open loop systems, closed loop systems, that you're teaching them, while loops, if, then, else. I know that the last couple of years, the questions that I've been charged with to write on the final included some control system stuff. So you don't want to dismiss that.
Okay.
And I don't know how long it would take to get the Robot C. I will tell you the full-blown Unit 3 will take you more than 3 weeks.
Right.
You can maybe get through the intro, not do the marble sorter, but get through some of the beginning units in those 3 weeks. But if you have some other program that you know and it's all good to go, that may be something that you stick with. But it took us a couple of weeks to get it took me a couple of weeks to get the code. Now it trickles down to me from other people. So, but yeah, and to be honest, maybe before your training, it would be more overwhelming than you can do in the 3 weeks anyway, to learn that coding language. Now, do you have another class next semester?
I have IED, POE, and civil engineering next semester.
Okay, so it'd be worth getting, because after you go to training, you're going to want it.
Yes, ma'am.
Okay. Somebody asked what I do instead of Bridge Builder. My kids compete in the Kansas University Pasta Bridge competition. And if you want those guidelines, just go to Engineering Expo, University of Kansas. And it's cool because my kids have built balsa wood bridges before. But pasta is an interesting challenge. So we do that as our culminating bridge activity. And it looked like Adam, I think, does concrete bridge or something.
Yeah, we create a like something more similar to what they would be used to driving over, like an actual concrete beam bridge that they would go through and design, and they'd have to think about strength of shapes and do some calculations and things on it. So applying a lot of that content from Unit 2.
Yeah. There's some good balsa wood stuff out there too. And you can break that if you have an SSA 1000, you can break that there. So, their other questions were about the final exam. Bill, I think you're with us. Maybe he's offline. Well, the question was if you can still use the formula sheet on the final exam, and the answer is yes. If somebody's referring to something they're not allowed to use anymore, my guess would be last year was the first year kids weren't allowed to use an 8.5 by 11 sheet of handwritten notes.
Cheat sheet.
And so people may be talking about that. Yeah, cheat sheet. So people may be talking about that, and I'm hoping they didn't use it last year because they weren't supposed to last year either. So, but Adam, will you show us the professional learning community? This is amongst your courses, and it is one of the places that I didn't often go to, but it's a really good source of information for what you do.
If you have your courses and groups set up like the way I do, I just try to have the only ones that I'm using up there. But if you go up to the View All or Customize, that'll give you all the ones that you're a member of. We're all a member of the PLTW, PLC, the POE OT, the POE Principles of Engineering, your whatever year in your school or your name. But the one we're talking about here is the PLC, the Professional Learning Community. And in there's a good bit of information. Some of the stuff in here is nice if you're thinking about getting into other courses and or opening up different programs in your school. But as you scroll down here, there's a whole section on the Project Lead the Way assessment as far as different resources that you might need. There is an engineering formula sheet. Again, we just talked about that. We can use it. For us, it's only like the first 6 pages that we really use, but it's one formula sheet for everybody. So if you do use that or print it off for your kids, I would just give them the section they need so they're not as confused. It does get into looking at frameworks, content mapping, and how they actually look at scoring the end of course exam, because again it's a stay 9, so the students will get a 1 through a 9 score on the USC, and it's similar in the way that they do to like an AP test where a student would get a 1 through a 5. Only a small percentage of them should get a 5, and a large percent of the largest percentage should get a 3. So if your students are getting 7, 8, 9s, they're on ours. That's really good. They're doing well. There is a forum down there to post questions too that you can access to help yourself out if you need to, or you can always email us and we can answer your question hopefully.
In there also, somebody asked about the dates of the testing stuff, and there is a calendar of dates of when you could. And so someone, I don't know if it's you or a district person or who, needs to register your kids into the test-taking program. You will then get a roster and codes so that they can access that test either in one 80-minute chunk or two 40-minute chunks. My kids take it over 2 days just because the way our classes fall, my kids have to take it over 2 days. So there's this manual, you can kind of look through it, and it probably answers almost all of your questions. Our district pays somebody to enter all of our students in and get their state codes and all of that. So I've never done that, so I don't know what that entails. Yeah, I don't know what that, well, pros and cons. The con is that I'm on their timeline, so
Yeah.
Really slows down the whole LMS situation.
Yeah. Well, the good thing is, the way it used to be, we were just entering them in for final purposes. Now all the students are entered so they have access to the LMS, and when they're entered into the LMS, then you're good to go. They're entered into the testing part as well. There's just a few more things you have to do to get them actually registered in that section, but that hurdle, which is the largest hurdle, is done. So for those of you that are getting ready for this coming up in January like myself, this is a good area for resources. If you're not worried about it until, May, April, June, whatever in that neighborhood, just try to keep this in the back of your mind.
Okay. I think I've answered everybody's general questions. Somebody typed a question, and I can't see what it was. So, Adam, while I'm working, I may let you go figure out what that was. Anybody have a question for the greater good before I start talking about the last PowerPoint in Unit 2.1? Everybody's okay? Okay, I am going to let Adam switch the powers to me here, and I am going to pull up the last PowerPoint in section 2.1. And it is calculating trust forces. We've talked through the activities through 2.1.5, and that was the one I talked about with the meter sticks and the weights and calculating moment. My kids just did that this week, and legitimately it took like 15 minutes to get them through that lab. So it was pretty quick. Now I had all the supplies laid out, but pretty quick to get them through that. There is an activity 2.1.6, which is a step-by-step trust problem. Most people I know don't use that. It's not a terrible opportunity to give a kid something that has some structure to it. One of the things that we're going to talk about is that there are lots of ways to do these trust force calculations, and that the step-by-step sometimes implies that there's only one way. So I'm going to just kind of start by talking through this PowerPoint, and then I'm going to move over to a SMART document and work through one of the trusses. When you go to training, one of the things that we spend a lot of time on is working on trust calculations. It has probably the most advanced math that we do, and it probably needs the longest attention span of any of the content that we work, even more so than the thermodynamics. So we'll talk through this. Also, if you are visiting my website, I've started videotaping my SMART, working the trusses on SMART documents and doing a videotape of that, so you can watch me working through the trust problems. And I started doing that this week. So if you go to yesterday's date, the 30th, you can see what we're going to work through right now. And then today in class I did just a truss problem I made up, and I'll continue to work those out if you kind of want to see a step-by-step of how I'm doing stuff. So this particular screen is really important. It talks about compression and tension. But one of the things that I do is I have 3 students come to the front, and I have one kid stand in the middle and kind of make a W shape with their arms, kind of elbows down and fists up. And they stand in the center, and then a kid on each side will just with one palm push on their fists and compress them. And I tell the kid in the center, don't let yourself be squeezed. So I want you not to let your arms, because what I want to also talk about is the reaction that that kid has to being compressed. Because the reaction to that external squeeze is for the member inside to react by pushing out. And then when they're in tension, I have them put their arms back in that W, and I have each kid grab with one hand and try and pull their fists out because they're in tension being stretched. And I say, what are you doing to keep your arms from being stretched out? And the answer is they're pulling in. So that is the guy in the middle's reaction force. And that's going to come and play here in just a little bit. Talking about trusses, and we've probably already seen this to some extent. It just talks about that it's just, members that are joined. This is a nice picture of a gusset right here. It's got welds and fasteners there, and it's a good opportunity to talk about the fact that most bridges fail at their joints, at their fasteners. It's rare that a big iron beam just breaks or a steel beam breaks. So that the joints are really the important part. So we talk about why triangles are important. Most of my kids have a gate on their yard. Most of our kids around here have a wooden fence. They have a gate, and I talk about the fact that their gate probably has like a letter Z on that gate, because just a rectangle, I can alter the shape of a rectangle without breaking any of the members. And a nice way to do this is if you take 4 straws and tie a string through them and kind of make this shape, you can take that rectangle and you can weeble wobble it all over without bending any of the straws. If you take that same situation of the straws and you make it into this shape, just run a Z shape through the middle, the only way that you can alter that shape is to break one of the members. So we talk about that. We have had this conversation before in one of the other PowerPoints, but important to know that a pinned support can have 2 potential reaction forces. So it can hold up-down reactions, and it can hold left-right reactions. And then a roller, it can only react perpendicularly to the way that it rolls. So it has 1 reaction force. We talked through the assumptions that we're going to make. Statics that we do is complicated enough without some realities to it. So we're going to assume the members are straight, that we're only applying loads at the joints, that we don't have any friction at those pins. Big one here, there's no weight on the members, right? Bridges are usually made of steel and concrete. This is definitely not true. And that our members are only going to experience tension or compression. If your kids have seen Bridge Builder, then they'll know that as the truck drives across the bridge that those members change from compression and tension based on their color. And it's kind of a good reference if your kids have seen that. So statically determinate. All of the trusses that we calculate are going to be statically determinate. It doesn't mean that you can't mathematically calculate trusses that are statically indeterminate. It's just more complicated. So all of our trusses will follow this rule. Twice the number of joints will be equal to the number of members plus the number of reaction forces. That means that we mathematically will be able to solve as long as it fits this. So here's a nice simple truss. This is actually the truss that we're going to work with. Currently, this truss, though, is statically indeterminate. So let's figure out why. We've got 1, 2, 3, 4 joints. So we have 2 times 4, which is 8 over here. And then members. Every time, one of the agreements we have is that every time we have a joint, we have a single member. So from A to D is one member, D to C is one member, C to B is one member, B to D is one member, and A to B is one member. So I kind of, if the kids have seen Tinker Toys, if I was to build this, I would have one of those Tinker Toy knobs here, one of them here. These are my sticks, each of these pieces. We have 1, 2, 3, 4, 5 members, so that would replace the M. The R stands for reaction forces. So this is a pin, that's our symbol for a pin, that triangle. So it has 2 potential reaction forces, as does this one, 2 more potential reaction forces. So we are now 8 equals 5 plus 4. So we know that we're in trouble because 8's now equal to 9. So the thing that we could do to make this statically determinate is to alter this right side of the formula by removing one of the reaction forces by changing this to a roller. Activity 217, which is the last activity of Unit 2.1, has 3 problems where they ask kids to take statically indeterminate trusses and change them into statically determinate. So one of the things they'll often do is change a roller to a pin, or excuse me, a pin to a roller. I do tell the kids you never want to fix this by making both of those rollers. A really good bridge that doesn't stand still is not a really good bridge. So you need to make wise choices on how you change those. So here's a picture of a bridge in New York, and if you took the time to count all those, you'd figure out that it is statically determinate. So this is the moment, and we talked about this. This is that turning force that we talked about, and that is the PowerPoint that goes with Activity 215. And there are some things that we agreed upon with the moment. We agreed that if the force turned the object clockwise, that we considered it to be a negative moment, and if the force had a turning movement that was counterclockwise, we counted that as a positive moment. That will come into play as we work. Summing the forces in the x direction for static equilibrium, we talked about the fact that all of the left pushes have to be countered by right pushes. We are going to declare go right positive and go left negative, which the kids are fine with. It's just like an XY axis. And then summing the forces in the y direction, so that up-down movement, same deal on this. All of the up forces have to be balanced by down forces. So up's going to be positive and down's going to be negative. So I'm going to show you where we're going. The rest of this PowerPoint walks through basically this problem. I am going to walk us through this problem on a PowerPoint so I can talk to you as we work. So this is what the PowerPoint does, is it will walk you through each of the components so you can practice this ahead of time and have this all worked out. Okay, we're going to go through this though as well. So that's what we're going to do now. Let me get over to my Smart document. The thing I like about using my Smart board is that it allows me to record what I'm doing, and then the kids can watch the work that I do on the board. If you have Smart availability, this little icon right here just has to be added to your toolbar, and then you can record all of your work. It records your voice and then all markings that are put on the board. The thing it doesn't record is you. So if you point at something physically with your hand, it's not going to notice that. So this is the truss that we just talked about. We've got a pin at A. We noticed that with the triangle structure right there. We've got a roller at C. We've got an applied force here at D, 500 pounds going down. We know this is statically determinate. This is the one we just worked with. So I'm going to kind of lead you through the step-by-steps that I use with my kids. So the first thing I do is I tell the kids that we're going to do step 0. And step 0 is where we label all of the reaction forces that are created potentially because of the attachments that we have. So here at A, we have a pin. And we know that that potentially is 2 reaction forces. So I'm going to go ahead and say that we potentially have a reaction force at A going up, down, so in the y direction. The vector notation that I use, just because of lots of physics that I've taken, instead of the whole arrowhead notation, I use a half arrowhead notation. So just heads up on that if you see that notation come. This full arrowhead is what you'll see in all the Project Lead the Way stuff. So we have a vector that's going up. That's at least my assumption. I'm not sure that it does. We'll know in our calculations. And I have another reaction, which could be a vector going to the right. I'm going to name this reaction force A in the x direction. Okay. The other thing, the reaction force we can have is here at this roller. So the roller is rolling left, right. So that means our reaction force has to be perpendicular to left, right. So I'm going to put it up. I'm going to call it reaction force C in the y direction. The fact is it's the only reaction force, but for continuity, I go ahead and note that it's in the y direction. So I consider this to be step 0, where all of those are labeled. And I tell the kids they can label that on the working document, on the problem that they're given. So if I give them a test or a worksheet, they can put all this labeling on the truss that they're given. But I do ask them then to do what I call a summary truss. And a summary truss is a place where they're going to put all of their answers cleaned up so that I can find what they're doing. Much of what I'm going to show you today is really about the process of them organizing their work so you have a chance of grading this. As painful as it is for the kids to do these problems, it's equivalently painful for us to grade these problems. So the summary truss will have the joints and the external forces that we know. So I'll have the kids draw a B with a circle around it representing joint B, an A with a circle around it representing joint A, a C. Notice these are in the locations where we find them on the truss. And right now the only force for sure I know is that there are 500 pounds pulling down at joint D. That's the only thing I know. I can't mark those other reaction forces because I'm not sure what their magnitude is, and I don't even know if they're pointing the right direction. So only things that are confirmed and calculated get to go here on this final summary graph. So that's something that I learned from a professor in Chattanooga as to how he had his kids' document work. Later in the PowerPoint, we are given some measurements that we need to know. I didn't want to show this to you right away because it's got the reaction forces already drawn on it, and so I wanted to go ahead and make sure I talk through that. So this comes later in the PowerPoint. What we know is the distance from joint A to D is 3 feet, from joint D to C is 7 feet, from vertically B to D is 4 feet. This angle here at theta 1 is going to be important to us, and the angle here that they call theta 2 is going to be important. Theta is potentially a new variable for your kids. They're probably used to x's and just calling it angle A, so prepare your kids to get used to that. So we've done step 0, which is to label all of the reaction forces. We've set up a blank structure, which I call our summary truss. And so now I have the kids do what I call step 1, and I ask them to number each of their steps so that I can follow their train of thought. If they make a mistake in one of the steps and then continue through, this way I can tell where that error happened and try and read through their work. So step 1 always is to deal with the moment. And we know if this thing's in static equilibrium that all the turn clockwise forces will be balanced with turn counterclockwise forces. And we know that moment is calculated by taking the force times the perpendicular distance. So one of the things we have to decide is where it is that we want to hold this truss to evaluate what the moment is. So what we are going to do is we're going to add up the turning forces at A plus the turning forces at B plus the turning forces at C plus the turning forces at D, and those should be equal to 0. But we have to hold this structure somewhere so that we know what is happening, whether it's turning clockwise or counterclockwise, because it will depend where that pivot point or that fulcrum is. So my recommendation to the kids is we want to hold where there is the most going on, and I'll explain why that is here in a minute. So my kids would say we should always hold at the pin, because we're either going to hold it at the pin, one of the supports, the pin or the roller in this case. My kids would say we should hold at the pin because it's got more going on. We have those two reaction forces versus just one. So kind of visualize, if I was to hold at A, and I ask the kids to let me know where they're holding, because you could hold at C. It would just look, the work would look different. So they're going to hold at A. So what they're going to do now is they're going to find the moment turning forces at A, at B, at C, at D. So is there anything that's going to turn this from A if I'm holding at A? Well, it's got a couple of things that potentially could turn it, reaction force AX, reaction force AY, but here's the fact. Both of those forces are located at A. So the distance those forces are from A is 0. So all of the turning forces at A have been neutralized. And I usually keep a piece of cardboard. I don't have it with me, but I've got like a rectangular piece of plastic that I hold onto, and kind of use that as my model for my kids to see. So I'm going to move this over for a second and go to my webcam. So like I'll have a piece of plastic or a piece of cardboard or something, and so I will hold, like our image is that we are holding at A. So then I'll say, what happens here because we are pulling down at B? What happens here because we're going down? What happens here? Is this turning clockwise or counterclockwise based upon what I'm doing? What we just decided was if I'm holding at A, if I push to the left or I pull to the right, it's not going to turn anything. If I push up or pull down there at A, it's not going to turn anything, and that's because those forces are 0 away from where I'm holding. So it makes sense that those are neutralized, and you can get that idea across the kids pretty quickly. So then we're just going to go through and we're going to look at all of the rest of the forces. So I would say I'm going to hold at A, and I would say, are there any forces by name or by number happening at B? And we don't have any external forces at B. So that means that there isn't anything pushing, pulling, anything at B, so it can't be turning. I'll say, is there anything happening at C? Well, we have a force that we denoted as pushing up. So if I hold at A and I push up at C, this particular object is turning counterclockwise or clockwise, and so you got to make sure you're looking at it is turning counterclockwise, which we have defined as a positive moment. Then we say, is there anything happening at D? I would say, oh, we got 500 pounds pulling down, so that would turn it clockwise, which we consider to be a negative moment. So that moment stuff that we've been talking about has been happening already. So let's fill that in. We have 0 turning at A plus 0 turning at B because there's no force to turn. Then we have at C, we have reaction force C in the Y direction. And we said when we held that that pushing up made that turn counterclockwise, which is a positive moment, times, that was an up-down push. So the question is how far left-right is our distance? And the answer is how far are we traveling from here all the way to here? And the answer to that is 10 feet. We don't label units on anything that's an unknown. Those units are derived and not dictated, so that RCY won't have a unit on it. So then we look at what's happening at D. So there is a force. It's 500 pounds. The question is, when I hold at A and I pull down like that, does it make it go clockwise or counterclockwise? The answer is it turns it clockwise. And so clockwise is what we consider to be a negative moment. That's an up-down force. The question is how far away from where we're holding it is it? And the answer to that is from here to here, and it is 3 feet. We know that that needs to add up to be 0. So we're going to have 0 plus RCY times 10 feet plus negative 500 pounds times 3 feet equals 0. So at this point, we're just going to solve for our unknown. So we have negative 1,500 foot-pounds equals 0. So I'm going to take RCY times 10 feet. I'm going to add 1,500 foot-pounds to both sides. Then I'm going to divide both sides by 10 feet. Those units cross off, those units cross off, those numbers cross off. We're left with, actually the 0 crosses off. RCY is equal to 150 pounds. And I noticed that it's a positive 150 pounds, which means, yeah, the direction that we drew RCY was correct. So I now have a piece of information. I can go up to my summary graph and say, oh, this potential reaction force here is going up, and it's worth 150 pounds.
And that's good, so because I was gonna say, a lot of when we do these stress calcs, a lot of the students have really big hang-ups on the direction of the arrow. And though it is important, if you go the wrong direction, you get the same magnitude of force. It's just a negative answer. So then you can tell right away. So I kind of let the kids be like, just guess. And if you get it wrong, this is how we're going to fix it. It's not that big a deal.
Okay. So we are now in a situation where we only have one left-right vector that is unknown and one up-down vector that is unknown. So we actually don't have to do any more moment calculations. And to be honest, we don't have any that we work with that you have to do moment more than once. Now, I personally ask the kids to box their work or draw a line so that I know where that piece of work ended and the next piece of work began. I got much better at grading these as I've had to grade a lot of them over time. So now I'm going to ask the kids to do what step 2, which is always the same for me. And that is we're going to sum the forces in the y direction. Those are equal to 0. And we're going to sum the forces in the x direction. Those are going to be equal to 0. So we're going to look back at our original. And we're going to say, okay, so what up-down forces do we have? We have at A go-up force that doesn't have a number, just a name. So we have a go-up force of RAY. I look at joint B. Joint B doesn't have any go-up, down forces, so I'm not going to worry about it. Joint C, I now know that joint C has 150 pounds going up. So I've got 150 pounds going up, so it's positive. And then I'm going to add to that what's going on here at D, which is 500 pounds going down. So down is negative 500 pounds. Okay, so I know that that needs to be equal to 0. So RAY is my only unknown. I have negative 350 pounds left over here when I combine what I know. So it turns out that RAY is equal to 350 pounds, and it is positive. So the direction that I drew that was correct. So I'm going to go ahead and do my X's, and then I'll go mark all this up on the board. So I look at all my left-right stuff. I only have one left-right force, and that's RAX. So I'm going to write RAX. It's going to the right, so it's positive. If I had some left stuff, that would be negative. So RAX, and this will panic the kids because there's nothing else there. The fact is that's the only force, then it has to be equal to 0. So here's the fact. That pin could stop something from pushing left or right, but because there isn't anything pushing left or right, it doesn't have to. So right now, the only thing I need to mark on here is that I have a reaction force going up of 350 pounds. I'm not even going to mark that left-right force at RAX because it doesn't do anything. So we now have accounted for all of the exterior forces, those that were applied and those that reacted to being applied. And we can see here, this is really easy numbers. We can see we got to go down 500 pounds, we got to go up 500 pounds. That makes complete sense. So now we are kind of to the hard part. We are to the point where we have some choices to make. And there are, I tell the kids, some good choices, there are some difficult choices, and there are some bad choices as to which joint we should start at. Because what we're going to do now is we're going to try and work on the interior, what the members are reacting with. So those interior reaction forces. So we're going to talk about the pros and cons of each of the joints. At A, we don't have to worry about this because that was 0. We have one exterior force right here. We have a horizontal member and we have a diagonal member. And we know that diagonal members are a little more work because we have to break them down to their horizontal and vertical components. But this one's not a terrible thing. We know something there. We can probably work through it. B, this is a terrible choice. This is going to get you nothing. We don't have any information at B. We have 2 diagonals, 1 vertical. I could say I'm going to go solve something at B, but I don't know anything about B, so I can't make any decisions about it. C is really equivalent to A. We've got just this one reaction force. We've got a diagonal. We've got a horizontal. Because we didn't have that left-right push at A, C is equivalent to A, so they're interchangeable. D has a lot attracting me to it. It doesn't have any diagonal pieces. I love that. It has a force going down, which means I'm probably going to be able to figure out the force going up. But I have 2 potential pieces here, go left, go right, and I know nothing about them. So D wouldn't get me everything I needed. So that's not a good choice right now. The fact is, I'm only going to have to do 3 of these 4 joints, and I'll have everything figured out. So I am going to avoid letter B forever. If I wanted to, I could ultimately do that last joint just to confirm my work. I'm usually just so glad to be done that I don't do that. So I'm going to box off step 2, and so step 3 is where I'm going to make a choice. Now I'm going to go ahead and choose to work around joint A. So I asked the kids to draw a free body diagram. This is why that word isolate is so very important, because we're going to just talk about what's happening at A. Right now, the only thing I know about A is that I for sure have 350 pounds pushing up. So I know that's happening at A. So I'm going to go ahead and mark that on. But then I have a couple other things that can affect A, right? So here's my joint A. If this member AB was to push up or down, it would move joint A. If this member AD was to push left or right, it would affect joint D. So I'm going to denote that those affect joint A, and they're going to make their mark on there. So this is when it comes into play why I had those kids stand. And again, I have one kid, you know, stand like a W, and I have either kids pull on it or push them in, and their goal is to not move with that. And so what we're going to do is called the method of joints. And the method of joints assumes that every member is in tension to start with. And sometimes I know that's completely wrong, but it is the technique. And I used to not use it. I used to say, we're just going to noodle our way through this until I caught at a couple of universities, and they said, this is what we teach at the university level. And so I thought I might as well, you know, convey what it is that they're doing at the college level. So method of joints says that we're going to assume that every member is in tension. If we remember what that is, that means my kid that was standing in the middle was being pulled out. So their reaction would be to pull in. So that being said, if this member was my kid in the middle and their arms were pulling in, then that's what their arms would be doing. If my kid was here standing between A and D, their arms would be pulling in, which is why I'm going to document the member's reaction force. And that is so hard for the kids, because as soon as I say tension, they want to say, oh, that means it's pulling out. The joints are pulling out. Not the case. So let's see what we've got. We are going to have to account for this AB. We're going to have to account for this AD. Remember that we're isolating, so we're only talking about what's happening there. So I had an AD that's a I'm going to denote it pull right because I'm going to denote it in tension. And I have an AB that I'm going to denote is go up and go right. I'm going to denote that in tension. Now, anytime that I draw a diagonal vector, and I've done this all the way from the beginning of the free body diagrams, I always had the kids, anytime they drew a diagonal vector, they always had to do the XY components. So this is a go up and go right. So there's my go right, AB in the X direction, and here's my go up, AB in the Y direction. So I now have all of the potential forces for A accounted for. So I can tell this is wrong. I mean, you guys can look at it and you say, you don't have any go down. I know that I need to go down, so I can guarantee you that ABY is wrong. But I'm going to mathematically show that to be true. That piece is a little hard for the kids. Again, I had a couple of people that had PhDs in engineering explain to me that this is the technique that they use. Both of them happen to be the deans of the civil engineering programs that I was working with. So that was word enough for me. So we're at this juncture. We're going to do the same thing we did before. We are going to sum the forces. The only force I know right now is an up-down force, so I'm going to choose to sum the forces in the Y direction. Same thing I did with the external. I have 350 pounds going up. That's this one right here. I should have written pounds there. 350 pounds going up, so it's positive. Plus, I have this vector ABY. It is also going up, so it's going to be positive, vector ABY. And I know that that needs to equal 0. That's all my up-down stuff. That red diagonal, I'm not going to worry about him because he's not a go up. I've got a black go up and a blue go up. So it turns out that ABY is actually equal to negative 350 pounds, which is great news because I knew that it was not correct to have that going that direction. So I want that to say, oh, no, that's negative, which means to us go the opposite direction. Kind of the negative yardage concept, right? So I know that ABY has a magnitude of 350 pounds, but instead of going up, it should go the opposite direction. Now the fact is, I am going to go ahead and leave that negative 350 and work it all the way through, because if I'm not going to redraw it, then I have to live with that. That's actually all the work that I have numbers for. So I really need to get some information about the X. So I have one side of this triangle right here and no other information on my picture, which is going to lead me back to this guy right here. This angle that I'm talking about needing, that's angle theta 1. And I have some measurements that have been given in this problem. The fact that this piece right here, the adjacent piece to that angle is 3 feet. And that this piece right here, that horizontal piece is 4 feet. That means I have the mathematical skill set to figure out that angle using trig ratios. So I usually have the kids document the acronym for the trig ratios, SOHCAHTOA. We talk about SOHCAHTOA. That's probably how their geometry teachers taught it to them. If your kids have not taken geometry, you're going to have to take time to teach them a little right triangle trig. My school has adjusted it so that they have to have taken geometry before they take POE, so that I don't have that issue anymore. So I know the adjacent, I want the opposite, that's O and A, so that is the ratio tangent. So the tangent of the angle that's called theta 1, if that really bothers your kids, you could always call it angle A, is equal to the length of the opposite side over the length of the adjacent side. So opposite side over the length of the adjacent side. Units will cancel. And then the question is, what is the measurement of the angle that has that? So the way that we undo tangent, the inverse operation of tangent, is called tangent inverse. Not a very creative name, but it's true. It's just like squaring undoes square rooting. That is the tangent inverse. You want to make sure that your kids are working in a degree mode on their calculator. A lot of my kids have calculators that are just set to radian mode and they don't even know it. So we're going to do the tangent inverse of 4/3. And it turns out that that's 53.1 degrees. And you're just going to have to make a decision how precise you want this to be. If you want to round to the nearest degree for your own calculations, that's fine. You want to round to the nearest tenth. I did. It was 53.13, and it kept going degrees. So that's how big this angle right here is, theta 1, which means clear down here where we are, this guy is 53.1 degrees. Now we're going to use that to our benefit. We now know one side and one acute angle of a right triangle, which means we can figure out the other side. So I know the opposite. I want the adjacent, that green piece. So that's, again, opposite adjacent, which is tangent. So the tangent of the angle, which is 53.1 degrees, is equal to the length of the opposite. You got to keep that negative 350 pounds because that's what we're working with, over the length of the adjacent, which is AB in the x direction. So I need to solve this unknown that's on the bottom. I'm going to multiply both sides by the vector ABX. And then I'm going to divide both sides by the tangent of 53.1 degrees. So I'm going to have negative 350 pounds, a negative number here. If we don't end up with a negative number, then we're in trouble, because if one component of a diagonal vector is backwards, all the components of a diagonal vector need to be backwards. And this turns out that this is 260, or negative 262 point, we'll call it 8. Negative 262.8, and the only unit left in there was pounds. So we now know that ABX, also the wrong direction. That's good news. So instead of being in tension, that baby should be in compression. We now have some left-right information, which is going to allow us to now sum the forces in the x direction. So we sum the forces in the x direction. See if I can get those pieces in this picture still. So if we sum the forces in the x direction, they should be equal to 0. We have a go right of ABX, which is negative 262.8. We've got to carry that negative around because that's what kept the go right with it. Plus, we have a go right, which is positive, vector AD. Those are the only left right. So we know that AD, when I isolate that, is going to be 262.8 pounds. Ah, that guy is drawn the correct way. So AD must be in tension. So I'm going to go back to my summary chart. So I know AD was correctly drawn in tension. So I'm going to go ahead and put those in. It was 262.8 pounds. And that is in tension. I also have information about AB. AB, oh, I don't have any information about AB. I've got its components, but I don't have information about it. So I need to come up with that piece AB right here. So I've got the opposite, I've got the adjacent, I've got the angle. I can either use sine or cosine. Either way, I'm going to go ahead and use sine. So the sine of 53.1 degrees is equal to the length of the opposite side, negative 350 pounds, over the length of the hypotenuse, which is AB. So I'm going to isolate the AB, multiply it to the other side, divide both sides by sine of 53.1. So I'm going to have negative 350 pounds divided by the sine of 53.1 degrees. I'm hoping that this is negative. There are other choices that you have. You can use the Pythagorean Theorem. For example, you have two sides. One of the reasons that I try to avoid the Pythagorean Theorem is kids forget that when you take the square root, you get a plus and a minus. So often they only grab the positive, and I need them to recognize that this answer is negative 437.7 pounds. Because I need to emphasize that this is drawn backwards. It should not be in tension. It should be in compression. So let me go back up to truss. It should be in compression, which means that it's being squished in, so it is pushing out. So my kid in the middle was pushing out when he was being compressed. I've already forgotten the number. 437.7 pounds, and that's in compression. So we got quite a lot from joint A. Adam, I'm going to let you make a call. Do you want me to stop here and we'll pick back up because we've got a few minutes left, or do you want me to go ahead and do joint D?
I mean, joint D is a real quick one, so mine as well.
Want to do it?
Yeah.
Okay. So what I love about joint D, I'm going to mark this off with all that work's contained. So this is step 4. What I like about joint D is it doesn't have any diagonal pieces, right? What we know about joint D right now is we've got 500 pounds going down and 262.8 going left. So we have 500 pounds going down, 262.8 pounds going to the left. What potential do we have to move joint D? Well, we've got this piece DC that could move it and this piece AD that could move it. I'm going to go ahead and draw both of those guys like they are in tension, right? So they're being pulled out, so they're going to want to pull in. I notice when I do that, that points, that always draws the vector away from the joint. So this guy and this guy is what I have. That's going to be BD here. And this is going to be CD there. So this is super easy, no diagonals at all. So I'm going to sum the forces in the x direction. I'll go ahead and do that. They need to be equal to 0. I have a 262.8 pound that's going to the left, so it's negative, plus CD has to equal 0. So CD is in tension with 262.8 pounds. Then I'm going to go ahead and sum the forces in the y direction. They're equal to 0. So I have 500 pounds that are going down, plus I have a BD, which is going up, so it's positive. That has to equal 0. So BD is equal to 500 pounds. So I come back up here, put that on what I know. I know, yes, this guy was in tension, and he's balancing with 262.8 pounds. And this guy, yes, was in tension. Those make complete sense based on the arrow notation. And so that's going to get there. The fact is we have one more joint to go. And when we finish up C, we'll have this entire truss calculated. So, Adam, do you want me to keep going, or what do you want to do?
Well, anybody out there want to finish, or if you want to? I mean, if you're good to go, stay another couple minutes and finish it. I don't think it's.
Okay, I'm going to go. It'd probably take me 5-10 more minutes to finish. So if anybody has 10 more minutes, let me go ahead and finish this. Does anybody have any questions before I keep going? I think Adam's been maybe answering some typing. Okay. Let's go on to vector C right now, or joint C. Right now we know we've got a push up of 150 pounds and a go left of 262.8. So I'm going to close off what I've got. There's a lot to be said for doing this on a chalkboard or a whiteboard because I am constantly scrolling up and down, which I'm sure is a little frustrating, but this is the only way that I can record what notes I'm taking for kids that are gone. So it certainly has its pluses and minuses. So joint C, 150 up, 262.8 to the left. Okay, so the only other thing that can affect joint C is very similar to what we had at A, and that is that this vector BC right here, that member, can push or pull on C. So we're going to go ahead and assume that he's in tension, so his reaction is to pull in. So again, tension is going to be away from the joint. I'm actually going to erase this 262.8 and put it below so it's not in my way. Okay, so I have this vector drawn in tension, and this was vector BC. Anytime I draw a diagonal vector, I'm going to need to draw its two components. I have a go left, which is named BC in the X, and I have a go up, which is named BC in the Y. So I'm going to do the exact same things that I've been doing. I'm going to sum the forces in the, let's go ahead and do the X direction. So I have a go left of BCX, so it's going to be a negative, that's my go left notation, of BCX plus a go left of, so negative 262.8 pounds, that has to equal 0. So it turns out that BCX is going to remain negative. So that means this particular piece is not, BC is not actually in tension, it's in compression. So I know that this piece right here, negative 262.8. So when I get a chance to go up to my summary chart, I'm going to change the direction of BC and mark it in compression instead. So now let's sum the forces in the Y direction. Has to be equal to 0. So I have a go up of 150 pounds, so it's positive, plus a go up of BCY, so it's positive, that equals 0. So good news, right? We said one of the diagonal components is negative. We need them all to be negative. So we get a negative 150 pounds. So it's still telling us that's the wrong direction. Okay, so now we're in a situation where we can come up with BC. Now, we can either go back up and come up with the angle, which would probably be my recommendation, or we could use the Pythagorean theorem. I'm going to go ahead, since I didn't use the Pythagorean theorem last time, do the Pythagorean theorem this time and just kind of talk through what I mean by both the plus and the minus. So Pythagorean theorem says that the leg of a right triangle squared plus the other leg of a right triangle squared, oops, units on there, is going to be equal to the length of the hypotenuse squared. So if we go ahead and crunch that out, when they are squaring these, they will turn up with positive numbers, just because that's what squaring does. And when we square root that, we end up with
302.6.
Thank you. Now, I'm going to end up with this answer, so let me get this other one. I'm going to end up with 91,563.84 equals BC squared. Now, when I square root both sides, the kids will kind of remember this. I teach a lot of math, so I can guarantee you they won't remember a lot of it. That is, whenever you square root, you get both a positive and a negative number. We want the negative version of that because we know that ours is backwards of the direction we want it to be. Both the components were negative, so this answer will be negative. That's the reason I'm a little sketchy on using the Pythagorean theorem here. So that's going to be 302.6 negative. We come all the way back up here. I'm not going to draw it in tension. I'm going to draw it in compression. So the vectors are going to be pushing out. The numbers are going to be pushing out in reaction. So 302.6 pounds in compression. So that's the one that goes with this PowerPoint. It does take you, obviously, a long time. We started it about 40 minutes ago. So that's how long it took us to do it.
Yeah, you definitely offer this over the course of a couple of, start at one day, one part of it, and then finish up another day. It'd be a lot to do in one period for the kids. They would just in minutes glaze over, and that'd be that. Yeah, so you can kind of do it in pieces. But the nice thing about doing it on a smart board or something like that is that you have your work from the day before. Mm-hmm. If you have that available to you. I share a classroom, so every hour my board gets erased. Anybody who's here, I'll send this out in an email.
We will meet in 2 weeks, which will be December 15th, and then we'll take winter break, Christmas break, and we will come back together then in January, on January 5th,
Yeah.
for anybody who's still around. That maybe exhausted them as well.
Now, does your smartboard, does it allow you to record your voice along with it?
Uh-huh. So yeah, it will record. The only thing it doesn't record is me. So I just have to be careful not to point at things with my hand. So you have to touch it. So that's just, that's a component you have to deal with. But you get better at that.
Cool.
Okay.